right, everybody. Welcome to this Wednesday where we be doing our first lecture. Get the link out for everybody so that they have it. Everybody is doing good today, so we'll try to keep this shortish, no more than 45 minutes. Try to shoot for a half hour, and we'll see how it goes. And of course, all these presentations will be recorded in YouTube, so they will be available immediately after the lecture concludes. So I'll be keeping an eye on the clock here. Let's give people a couple seconds to get in. If we will have anybody joining us tonight. Connection looks good. Okay, so like all the lectures, or all the YouTube presentations, there's two methods. You can ask questions in the right-hand box on the side of the YouTube video, or you can do the Discord server, and or you can do the Discord server in the YouTube channel bio. And I will try to be watching both. But that is how to ask questions, and if I can answer them, I will. Okay. So, not that many slides. We'll run through them here, and then we'll talk next steps. So, programmable logic controllers, also commonly known as PLCs, are really a fundamental building block of all industrial machinery and factory floors and industrial automation. You really can't, if you're going to be any kind of field that involves industrial automation or manufacturing or mechatronics, you really can't avoid the programmable logic controller. It's really the most basic building block, again, of what's happening out there. You'll see them everywhere. On a typical factory floor, you'll see them anywhere, blinking lights and everything. And if you gain an understanding, a deep understanding about how they work and how to program them, and even how the electrical cabinet for machinery is structured, you can go a very, very long way in the industrial automation space. So that's the whole point. We're going to start with PLCs as something relatively simple on the factory floor, and from there we will graduate into more complex controllers. But this is a basic one. So today we will talk briefly about two major groups of industrial computers, really my grouping, more or less, but it's not too far off reality. Basic structure and operation of the PLC. We'll get into very high level things today, but in the future we'll dive down deeper by necessity, and then we'll talk about programming languages that these PLCs generally support. Okay, so a bit of, trivia, I suppose. The first controller that resembles how the modern day PLC looks and operates today was specified, or it was desired, by the Hydromatic division of General Motors back in 1968. The first product emerged in 1969. The General Motors wanted to better automate their production line for automatic transmissions. And in the past, they were using very crude relay switches and things like that, but they wanted a solid state controller that had the flexibility, reusability, simplicity, durability, and modularity of what we enjoy in today's modern PLC. So that's how old these devices. Now they've evolved considerably since then, but that is where their origins lie. Okay, so one on the left, one on the right. The one on the left is programmable logic controllers, or hard PLCs. And we have programmable automation controllers on the right-hand side, which is grayed out because it'll be a little bit before we talk about those. Those are a more complex controller. I would say considerably rarer controller, but what programmable automation controllers are basically are industrial computers that look a whole lot like regular consumer personal computers, ones we're all familiar with. They're generally smaller, so they can fit in an electrical cabinet, and they're industrial hardened, and they're certified for industrial uses. But most of them feature good old standard Windows, Microsoft Windows, and they even boot up into a Windows interface. And so really what you have there is a system that you can program in nearly the same way as you can write programs for a regular consumer PC. Of course, they're going to be industrial programs, but the set of programming languages you can use are, virtually limitless. And the other thing that programmable automation controllers often feature is a software-based runtime layer and associated development tools that allow you to build motion controllers and other logic controllers, and you can do quite a bit of customization there. CNC, they usually include like a CNC motion control package that can read in G-code files and output. So if you're doing like a custom vertical milling center or something, you can, and you're designing that kind of machinery, you can slap on a programmable automation controller and get that CNC functionality for quote unquote for free. I mean, you're paying for it, but it's built in, or it's otherwise compatible with the programmable automation controller. And so that is a distinct entity from a programmable logic controller, which we are going to stay on for quite some time. Programmable logic controller is a lot simpler. They're dedicated hardware that supports usually a fixed set of programming languages, and they're really only dedicated to one thing. Now there's been some overlap in recent years where programmable logic controllers have gained some motion control functionalities and such, and we will dive into that later. But for all intensive purposes, we will be sticking with the simpler, dedicated, domain-specific programmable logic controller, and then we'll graduate to the right side in time. See if there's any questions. None yet. Okay, so let's kind of back up a bit and look at what we're dealing with, because fundamentally we'll be dealing with this diagram quite a bit, way beyond a conversation about PLCs. But in the real world, there's a physical process. There's a automation line, there's a machine, there's some sort of activity that's happening in the physical realm. And decorated around this machine or production line are sensors. They sense whether there's a box in front of something, or what temperature something is at, or how the wind's blowing, or anything physical. And those measurements are fed into a controller. Then the controller does something, makes decisions based on what it just measured from these sensors, and it outputs control commands to impact the physical environment in a controlled manner. So you're doing useful work that way. You're doing useful work. You're measuring the real world. You're making decisions based on what those measurements are, and then you're impacting the physical world in a useful way. That's the basic structure we're dealing with here. And we will see this represented quite a bit across nearly everything we talk about. Okay, so in terms of kind of putting a bow on this, I mentioned devices, sensors. The middle box here that has the power supply on the left and the memory on the right and the CPU in the middle, that represents the PLC, a controller. A controller has a power supply to power it, and any inputs and outputs connected to it in general. And then it has the concept of memory. And both of these, the memory will become extremely important because in most PLCs, inputs and outputs are read and updated through memory addresses. And so we'll spend a lot of time on, in subsequent lectures, we'll spend a lot of time on PLC memory and addressing. But some examples of digital inputs and analog inputs. Okay, so digital inputs you can think of as 0 or 1, on or off, open or closed. Two states only. So you have a push button on the table. The button is either not pushed or you're pushing it. Open, closed. Selector switches, proximity sensors. This is not an exhaustive list, but these are examples of various digital inputs that are available to hook up to your programmable logic controller, available for your machinery. Limit switches and photoelectric sensors. And then you have analog inputs, which are continuous. So digital inputs are discrete, 0, 1. Analog inputs can operate over a range of values continuously. So you could have a position sensor measuring some kind of distance from one point to another. Maybe you have a moving table. Okay, and there's constant values. There's a steady stream of values being extracted from this sensor and being piped into your programmable controller. Okay, and then to the PLC, you can have multiple. PLCs they generally support multiple inputs connected to it. So you don't have to pick one. You can have multiple, and when we're dealing with non-trivial machinery, the whole machine will be decorated with sensors galore. And we'll have to size the programmable logic controller appropriately, either one or multiple controllers, to handle the input from these devices, these sensors. Okay. Then again, as I described in the last slide, the CPU, through a predetermined program, executes some logic based on the input it's seeing from these devices. And then it outputs to things like solenoid valves, position valves, lights, turning a light on and off, various other actuators, motor starters, and again, this list is not exhaustive. So you can imagine someone walking through the door, right, and there's a photoelectric sensor in the door. So like a light curtain, like an invisible beam. And once you break the beam, right, the photoelectric sensor turns on. And then you could have some logic in your controller to say, okay, when that light is broken, turn on a light somewhere. So you're taking it in input, you're doing some logic to it, and then you're affecting the real world. You're doing some action that impacts the real world. Okay, this is a three-dimensional representation of, and now I have gone over to Onshape. This is a 3D representation of a programmable logic controller. Okay, they come in various shapes and sizes. This one is a microcontroller, which is rather simplistic, but there are higher end PLCs that again incorporate many, many more inputs and outputs and various other capabilities that for now we will sort of not touch on, but in the future we will. And what you see up here are flathead screws for flathead screwdrivers. And then you can put wires in each of these openings and then tighten them up with the screws. Okay, so you have a row of inputs up here and you have a row of outputs down there. Okay, so this is where the wires go. All right, don't worry about the details too much right now because we will go through this in some significant detail, but that's where you put the wires from all your sensors up here, and then your signal wires for your actuators are down here. These are the outputs. And so in the middle here, you have a power supply, in this case supplying 24 volts. Generally, PLCs come with two options. There's either a 24 volt option or there's a 120 I got a message here on my live stream. Let's see. Yeah, so either it's 100 or it's 24 volt DC or it's 120 volt AC as usually it. We will not be talking about the higher voltages that much. I have not personally in a long time come across 120 volt PLC in my machinery. There are certain safety characteristics associated with that type of power supply that I am not that acquainted with, and so I won't personally be talking about it a lot, but there may be others that I can find that can talk more on that. But I'm not competent in that, so I won't be talking about that. I would say that as time goes on, for quite some time now, a lot of companies are shifting over to DC 24 volt power supplies. So that's what we'll be using, and that's what's here. Then this box right here represents the CPU and the memory, if you will, the actual controller. And there's some indicator lights on here for various states of input and output. And then on this model, there's two dummy. These are actually dummy plates. You can take them off, and you can put modules. Depending on your application, you can put additional modules in here, in these slots. So there's one slot, there's two slots. Okay, we'll be talking quite a bit about that as well in time, because there is a ton of options. I think for this particular product, there's something like 20-ish available modules you can buy and plug in here. You get two spots, one spot and two spots. Okay, and then there's a micro SD card reader in the back to do programs. I believe this one also supports programming through Ethernet. So there's an Ethernet port down here. So yeah, we will be, with this controller specifically, we will be spending a lot of time talking about it. And then in future lessons, or future lectures, I guess, we will be doing, this is an electrical cabinet, and it's mounted on the side of a machine, and you can see the controller in there right now on a DIN rail, DIN, DIN rail. And we will be wiring this whole, there's more to be put in here. More wires, more components. And we'll be wiring the whole thing up, and I'll have to show you how that's done, basically, in subsequent lectures. But for now, that's adequate enough right here. Just the single controller, and then later on we'll populate the rest of this cabinet. There's actually a door to this. I just hid the door, so the door's closed now. Okay. All right, so again, we're scanning inputs from our input devices, from our sensors. We're executing a program in the controller against those inputs, and we're updating outputs. Okay, and there's a cycle happening here, a very, very fast cycle. It's usually on the order of 3 to maybe 50 milliseconds. The scan time, the time it takes internally for the inputs to be scanned, the program to execute, and the outputs to be updated is known as scan time. And I'm sorry, I got some noisy cats in here. Excuse me for just one moment. Sorry about that, everybody. Got some cats rambunctious in here. Anyway, so the inputs are scanned inside the controller, the program's executed, and the outputs are updated. That time that it takes to do that is known as scan time. And again, it's like 3 to 50 milliseconds, so very fast. And then the loop begins all over again. Inputs are scanned, execute program, update outputs again. Every, could be 3 milliseconds. Just like that. And what needs to happen there in real world industrial applications is that you will want to understand what the upper limit of the scan time is, which can be influenced by the number and type of inputs that you're putting in and the outputs that you're supporting. So the controller itself is certified and structured from a software and hardware point of view such that the scan time is predictable given a set of inputs and outputs, types, and number. Okay, so I think that's the best way to describe that right now, but we will look at that issue in detail once we start handling actual inputs and outputs. There's a plot. There's a series of plots to discuss in terms of scan time that are influenced by, again, the inputs and outputs. But it's very important to realize that this right now. It's very important to realize that this cycle is happening very rapidly in the controller. This loop. So it's constantly doing this. So fast you can't really see it in the program environment that we will be exploring in subsequent lectures, which is visual nature. Okay, so programming languages. These, if you are not familiar with programming, if you're familiar with programming in general for like personal computers, these programming languages will seem odd. They are designed, most of them are designed to be visual because it is easier for technicians to relate the visual nature of the programming environment to the actual physical structure of the factory floor or the machine. Sensors are represented by blocks For example, outputs are represented by certain symbols, and so most of these programming languages kind of try to keep things pretty visual. It's also good for a visual programming language is also good for technicians that may not be really familiar with higher level programming languages in general. So, there's not generally computer scientists or people classically trained or experienced with programming languages on the factory floor. They need something a bit more obtainable. And so a lot of these programming languages try to do that in their very design. These are, I think, in order of at least what I consider most popular at the top, least popular at the bottom, or most encountered at the top, least encountered at the bottom, if you will. The first three programming languages, ladder logic, structured text, and functional block diagrams, are in bold text because those are the ones that, at least for the foreseeable future, I will be talking about in some detail. These are ladder logic is by far, I think, the most popular. You're going to run into that one everywhere. But structured text and functional block diagrams are starting to emerge for more complex machinery. And there's some advantages there in using those programming languages. But for now, we will be focusing on the ladder logic part of this, the ladder logic programming language. And if you ignore everything above this line here, this line I'm drawing with my cursor, this here represents what a single rung of a ladder logic program will look like. There's two rails on either side. On the left side, there's inputs, and on the right side, there's an output. Okay, what these two rungs up here represent is the physical situation. So you can see here that there's you can call this a push button, right? I'm pushing on the top of this part here, and it pushes down this line here to make a connection. And you can imagine some voltage. Maybe this is 24 volts over here, and this is ground. And when you push the button down on either of these buttons, current will flow through this wire and the light will turn on, right? So that's represented here. You push down the button, current is now flowing through here, and the light output turns on. So input button, output light. Okay, so these two rungs here, you could think of like rungs on a ladder, right? Ladder logic, you could think of rungs on a ladder. So these two rungs here represent a physical situation. They will not be in a ladder program. This rung here, this bottom one, is what you'll typically see in a ladder logic program that represents this physical situation. So there's a symbol here with an address of 30, a memory address of 30. This represents a light output. Okay, and there's two normally open blocks here. Okay, so while these blocks are false, meaning that the button up here is not pushed, this light will remain off. once one of these buttons, you can see that they're connected in parallel here. Once either one of these push buttons is depressed, either one of these blocks here will toggle to true. And that will mean that this whole rung evaluates to true, and then the light will turn on. So that is what ladder, and that there are many, many, many symbols associated with a non-trivial, many symbols, and there will be many rungs to a ladder. I have a book on my desk here for a Toyota CNC vertical milling machine, I think. And it's 50, maybe even 75 to 100 pages of just ladder logic for the machine. Page to page ladder logic. Thousands of rungs, tens of thousands of symbols probably in there. All for one machine. So these programs can become, this is only one rung, but we will be dealing with programs that have many, many, many rungs. And to help you out with that, most PLCs ship with their own integrated development environment where you can write, you can drag and drop and create these rungs with a visual interface, and then you can simulate, I guess, the nature of your program, and the inputs and outputs will light up as your program executes. So again, a very visual programming environment is supported by all or a vast majority of PLCs. So ladder logic is a great place to start, and we will be, don't sweat the details that much yet if you don't get what's going on here. It's something that requires a very visual approach, and we will have to create tools that I will open source. I intend to open source that will demonstrate that we can all use on our web browser at home, that will demonstrate how to write PLC programs with ladder logic. It's a very to really grasp it. I'm going to do lectures with slides here, but to really grasp the details, there will need to be a sufficient amount of hands-on activities to do it. It's one thing to show it, but it's another thing that we'll have to, you have to interact with it to really understand it, just like anything else, but especially here, I would say. Okay, clear as mud. I think that's it for me today. So, let's see if there's any questions. I don't think so. Could be pretty late for everybody. There's 3-4 viewers. We had some more previously. Probably got sick of hearing me yap. Someone in the Discord the other day, Clockmaster, I think, recommended that I do a pathway, that I show a pathway of learning, of where we're going with these lectures. I was going to do it, but I ran out of time. But for next lecture, where we will dive into ladder logic programming, an introduction to ladder logic programming, I will have somewhat of a pathway for that, basically showing where this ship is headed, because I think it's a good idea that if you know where this train is headed, you might stick around and want to learn how to do this stuff. So next lecture, I'm going to try to do a lecture once per week. I wanted to try to do 2 this week. I don't know if I'll get to it, but I want to do at least one a week. And by the end of the year, we should be in a pretty good spot to hit the ground running after the holidays, basically. So anyway, thank you for joining me. If you are tuning in live, if you are watching a recording, thank you for tuning in just the same. Any questions that you have, you can ask me in the next minute or so. If you want to join or ask questions or have comments afterwards, I'd recommend the Discord chat server link in the YouTube channel bio. And I am in there 24/7-ish. Sort of like the central hub for everybody. I kept it pretty brief, 41 minutes. I'll take it. I don't like to go over 45 minutes with these things because people start tuning out. But yeah. Okay, well, thank you. And if you either have a good night or, depending on where you're at, a good morning. And I will see you the next time. Thanks.